Welcome everyone. Today we'll be examining a groundbreaking paper in the field of computer vision and multimodal learning. The paper, titled 4M-21, an any-to-any vision model for tens of tasks and modalities, was authored by Roman Bachman and colleagues, and was published as an Arxiv preprint in June 2024. This work represents a significant leap forward in our ability to create unified models for diverse visual tasks. To appreciate the significance of this work, we need to understand its context. Historically, multitask learning in computer vision has been plagued by issues such as negative transfer and the need for intricate loss balancing strategies. While recent multimodal models have shown promise, they've been constrained by the number of tasks and modalities they can effectively handle. The authors of 4M-21 set out to address these limitations by creating a unified model capable of handling an unprecedented range of tasks and modalities without compromising performance. The 4M-21 model introduces several key innovations. First, it expands the scope to handle 21 diverse modalities, a substantial increase from previous models. This is achieved through sophisticated modality-specific tokenization techniques, enabling the representation of various data types in a unified format. The model employs an advanced multimodal masked modeling approach for training, and crucially, it's co-trained on multiple data sets to enhance its generalization capabilities and robustness. The range of modalities handled by 4M-21 is truly impressive. It encompasses visual data like RGB images, geometric information including depth and surface normals, and semantic data such as segmentation maps and bounding boxes. The model also incorporates learned representations from state-of-the-art models like CLIP and DNOV2, various types of metadata, and textual information. This diversity enables rich, multimodal interactions and opens up new possibilities for complex tasks like cross-modal retrieval and controllable generation. A critical component of 4M-21's success is its sophisticated tokenization strategy. For image-like modalities, the authors employ a VT-based VQ-VAE to create a grid of discrete tokens. Vector data, such as global embeddings or 3D poses, are processed using MLP-based discrete VAEs. Text and other structured data are tokenized using a word-piece tokenizer. This unified tokenization approach allows the model to process all these diverse modalities within a single architectural framework, a key factor in its ability to perform any-to-any operations. Let's look into the training methodology. 4M-21 utilizes a multimodal masked modeling objective, where the model learns to predict masked tokens from unmasked ones across all modalities. Notably, they co-train on multiple data sets: CC12M for modality diversity, COYO 700M for scale, and C4 for enhanced language modeling. The authors implement diversified masking strategies to address various training requirements. The largest variant of the model scales up to 3 billion parameters, demonstrating the scalability and computational feasibility of this approach. The results achieved by 4M-21 are remarkable. Despite handling a significantly larger number of modalities, it shows no performance degradation compared to specialist models or previous multimodal approaches. It demonstrates robust, out-of-the-box performance across a wide spectrum of tasks, often matching or outperforming task-specific models. Furthermore, it enables novel capabilities in multimodal generation and retrieval that were previously unattainable. One of the most exciting aspects of 4M-21 is its advanced multimodal capabilities. It can perform any-to-any generation, effectively generating any modality from any other modality or combination of modalities. The model allows for fine-grained controllable generation using metadata, providing unprecedented control over generated outputs. It also excels in cross-modal retrieval tasks and demonstrates improved text understanding compared to its predecessors, bridging the gap between vision and language models. Despite its groundbreaking achievements, 4M-21 does have limitations that point to future research directions. The authors note that the model's transfer or emergent capabilities, the ability to solve novel tasks not encountered during training, are still limited compared to large language models. There's potential for further refinement of tokenization strategies and opportunities for even larger-scale co-training on more diverse datasets. The significant computational resources required for training these models also present ongoing challenges that need to be addressed. To conclude, 4M-21 represents a significant advancement in the creation of a unified vision model capable of handling a wide range of tasks and modalities. It demonstrates the feasibility of scaling up to tens of modalities without sacrificing performance, opening up new avenues for multimodal AI research and applications. However, it also highlights ongoing challenges in terms of computational resources and the quest for true emergent capabilities in vision models. As we move forward, it will be fascinating to observe how these models evolve and what new possibilities they might unlock in the fields of artificial intelligence and computer vision. Thank you for your attention. Are there any questions? Leave them in the comments below.